All right, so we'll be talking about the number derivative, as I've written on the board. So a good place to start is let's define it. So in 1950, this came up as a Putnam exam problem. There was a mapping defined with two properties. So you have three maps, natural numbers, integers. Any prime p. P takes p to 1. And this, the derivative of a times b, or sorry, the phi of a times b equals a times phi of b plus phi of a times b. So this looks very much like the product rule from calculus. And that made Barbeau in 1961 give it the name the number derivative. So, first thing I'd like to do is use this definition to give a quick example. So, phi of 6 times 3. According to the product rule, this is 2 times 3 plus 3. These are both 1. So it's 2 plus 3 or 5. Alright. So this is fun. We have something from natural numbers effectively into themselves. The one thing that I left out here is 1. So let's figure out that. So what is phi of 1? Or we'll say the derivative from now on, since it's the number derivative. The derivative of 1, well, 1 is 1 times 1. So that's 1 times 1 plus times the derivative of 1. Well, if phi of 1 equals 2 phi of 1, phi of 1 equals 1. Alright, so we have a definition. So, what do we do with it? Well, first I would like for you guys to just play around with it a little bit. So we'll do a quick class activity. I want you to find the derivative of 33, the derivative of 12, and the derivative of 27. So I'll give you a couple minutes. It doesn't matter. We can do it in groups, you can do it by yourself.
So there are multiple ways of breaking, say, 12 into, different number of ways. How do you use that definition?
So that's very good. So you can break it up. So we'll do 12 really quick, since that's a strange one. I'll do 12. You can work on the other two while I'm doing it. So 12. So there's a couple ways you can break up 12. Let's just look at two of them. We have 4 times 3. We have 2 times 6. We'll do those two. So this would be 4 times 3 plus 3 4. Yeah. So we know this is 1. And we can do the same trick with 4 here. Split this up. So 3 to 4 equals 2 times 2 equals, just to be quick, I'm going to ignore the fact that the primes are 1. So it's 2 plus 2 is 4. So 4 times 3 3. So we have that this equals 4 times 3, which is 12, plus 4 is 16. If you do it with 2 times 6, you can do the same thing. Just break 6 up into the prime components and do the same thing. So we have this one, 12 is 16.
And we are guaranteed to have the same answer every time.
Yes, you are. Yeah, I'll go over that. It has a well-defined definition as well. So does anyone have an answer for 33 yet?
14.
Murphy.
14.
14. Very good. 33 is 3 times 11. 3 plus 11 is 14. Nice. How about 27? This is a pretty good one. Yeah,
27?
27, good. So that one's interesting. You saw, I don't know if you remember seeing it, but the same thing happened before, and we'll talk about why here now that we are going to show that it's well defined. So let's see. In what year is that? I don't have it written down. Okay. Somebody at one point showed that this was equivalent to this. So, another definition, we'll say. Also, notation. Because of it being a derivative, we're also going to let phi of a equal a prime. So we'll, and for most of the talk, I'll use a prime notation instead of the phi, because it's just a lot easier to write. All right, so the definition. Now, hold on. Before I write this down, I want to point out that these are very specifically related to their prime factorization, what their derivative is. And so it makes sense that we would use the fundamental theorem, fundamental theorem of arithmetic, that all numbers have a unique prime factorization. So, if n is the product, okay, of primes p sub I to some exponent, times p and x sub I in, we'll say, in the natural numbers right now. This is kind of an important point we'll come back to. So if this is what your n is, then n prime equals n times the sum equals 1 to x sub I over p sub I. So here we have a definition. Let's show that it meets those requirements over there. So if our n equals p, it's pretty obvious to see. We have n prime is p times 1 over p is 1. So that one comes out pretty cleanly. Now let's see if we have two different numbers that, if n is a product of two numbers, that it comes out to what we want. So let a equal product 1k a sub I, and b product equals 1k b sub I. Now notice that these are the same case. We're just assuming that these exponents, sub I or b sub I, could be 0. So just to have all the primes correspond to both of them. So then when we have the product, we have AB equals, AB prime equals A product 1. B times some, break this up since that's condition. A, B sub B sub I over B sub I. derivative of b derivative of a, it corresponds, right? In just the right way. All right. Now, what I want to do, I want to beat this up, so don't let me erase this. All right. So, now that we have this, let's talk about why we care. What can we do with this? What's the motivation? Now, the motivation, I'm going to skip over some of the properties, but we'll go back to those. The main motivation is what we call number differential equations, or NDEs. So let's see. Let's give an example. The most natural example is n prime equals 1. Sure. If n prime equals 1, based on our definition, and we can actually show uniquely that the solutions are n equals prime. All right, so that one was easy. Let's see, example 2. Let's do n prime equals n. Now this goes back to this question right here. When is the derivative the same as the original number? And again, we can show uniquely that this happens when n equals p to the p. And let's see. I could go through the proof of this, but it's not that important. So this is why it works for 27, which is 3 cubed. It also works for 4, which is 2 squared, and so on and so forth. An interesting question, which I think I'll leave open just for you guys to think about, is how does this relate when you have something like, well, I'll write it over here. N equals 108, which is 2 squared times 3 cubed. Is that going to be the same as 108? Is it going to carry over, or is it going to have some connection to it? This is an interesting question that I spent some time on. Just something to look at. All right. Then the really motivating one is the general case. So, example 3 and everything after that. N prime equals a for some given a. Now, why this is interesting? Why this is interesting is that we can recast some of the conjectures of number theory into this form. One of the examples is Goldbach conjecture. And let me grab my paper so I write it down correctly. The Goldbach conjecture states the following. Even number larger than 3 is sum of 2 times. So, written more succinctly, that is that 2b or NB times, not any price, but specific terms. All right. So, how can we recast this? Well, let's see. If n prime equals 2b, if that's our differential equation, our NDE, then this is true if the solutions to this n equals PQ for all b. So for any b, if we have a solution to this equation that is n equals PQ, then that would verify Goldbach's conjecture. So we have a recasting in different terms in terms of the number derivative. So that's interesting. Let's see if we can do it with another one. So let's do the twin primes conjecture. This says that there are infinitely many prime pairs P and P plus 2. So where P and P plus 2 are both primes, the conjecture is that there's infinitely many of these. So, examples 17, 19, and so on. Now, this one has the differential equation. This one's actually pretty interesting. N double prime equals 1. So this is taking the derivative twice. Derivative, which Alright, so I'm curious if anyone can see why would this be the case. Oh, hold on. Let me tell you what the solutions would look like. So this would prove this if the solutions, if there were infinitely many, solutions of the form n equals 2p. So can anyone see why that would prove that? What is the derivative of 2p? 2 plus p? Alright. And if 2 plus p prime equals 1, what does that say about 2 plus p? It says it's prime number. So again, we have this connection between the number derivative and a conjecture of number theory. So this is interesting, and there's actually other examples of ways that we can recast. It gets a lot more complicated and more difficult in conjecture. But with this framework, it'd be interesting if we could come up with a way to work in reverse and take the number derivative definitions and work backwards to getting the solutions to some of these conjectures. So that brings us to what we're really interested in. Now, it's fun to play around with the number derivative. And after I get to what we're really interested in, I'll show you some of the fun attributes of it. But what do we really want? Well, if we're going to carry this analog, this analogy as far as we possibly can, the derivative, then what are we looking for? We're looking for a number integral. So, number, we'll put that in scare quotes because who has any idea what that means? Alright. Now, there are actually two ways that we can define this. Because the solutions to any given n prime equals a, because these solutions are not unique, there could be infinitely many, there could be 0, it's non-trivial how many solutions you get. So we can define the integral in two different ways. The optimal way, what we want to find, is this big I of a. Right? which is the set of all n such that n prime equals n. So that's what you really want to get. That would be beautiful. You could just throw everything into this big hammer and pull out solutions to really complicated number theory problems. But a more realistic thing that we were looking for is the little a, which is just the number of solutions, or the size of big I. And this is a little bit more reasonable. Now, this is my main motivation for tinkering around with number theory. And we'll give a quick little teaser for my Eminem talk. So, teaser that I'm going to be talking about my methods of trying to figure this out. So, if curious, do you ever know?
Yeah, on December 10th.
December 10th. Recently changed. All right, there you go. Now, for this talk, we're not going to get too much into I of A. We'll do a quick note because it's interesting. And I should have time, I'll show you that the number derivative itself is actually bounded. But this I of A is not bounded, it's bounded in general. So I of A is not bounded in general. Which makes sense. I mean, for one, it's infinite, so you would expect that it would be kind of chaotic.
Can you give an example of one that is bounded?
One that is bounded, so there are a number of numbers that actually have no integral. So solutions to, I erased it, n prime equals a, there's no n, so no solutions. I'm trying to think, I know a lot of them are primes. So there's like, I think 19. I don't think there's any solution where n prime equals 19. Up to 998. I know it's been checked all the way through 1,000. At one point, checked it higher than that, but I don't remember anything I found. But yeah, so which seems kind of strange, right? That there are numbers that don't have an integral. That when you do this derivative process to other numbers, you never reach that one. But again, we'll go a little bit more in depth on that in our talk when I have more time to. So, for the rest of this talk, I want to just go over a few properties of the number derivative. Now that we have motivations, you actually have some reason to care about it. Let's look at it, because it's kind of a cool thing. So, we'll erase gold block and twin flash. We'll just erase the conjectures. So we'll go back to this bounded point. The first properties. So the first property that we'll look at is that n prime is bounded. All right. Now this was shown, to my knowledge, it was shown by Westrick. I think she's the first that showed this, and this was in 2003. So I'll just throw up what the bounds are. Well, let's write it formally. So theorem. This is math. Let's have some theorems. If n is a sum of all these exponents. So this is like the number of factors. So the number of factors of n. All right, and this is, if you give this k, then n prime is bounded by k in k minus 1 over k less than or equal to n prime to 2 to the k minus 1 plus k minus 1 over 2 times it. Alright. Oh, that was a terrible sound. Alright, so this kind of comes out of nowhere, but I'll prove this one. This one's a little bit more involved, so I won't worry about the upper bound. But what's really interesting here is that in both cases, the bounds on our derivative comes from the number of factors of that derivative. So how many primes are composed to make this number. And that's a really interesting thing that I will show you a cool picture of in a minute. All right, so why is this the case? So, proof. So this is proof of the lower bound. So let's say that n is the product equals 1 to k of p sub I, and we're going to assume that there's no exponents on this. So we're just looking at p sub I, and this allows p sub I not necessarily distinct. So you could have, multiple 2's in a row. It's okay. That's what we're dealing with. Though. We have some string of p's. So that k is the number we're looking for. Then n prime equals n times 1 over p sub I p1 plus 1 over p2 plus p sub k. Now this is minimal if all the p sub I are the kth root of n. So if, for instance, it's 2 to the 6th, then we have 6 1/2s, and this ends up being, so this implies n prime is less than or equal to n times k over the kth root of a, and this is just equal to what I have written over there, k n to the k minus 1 over k. And since we did this little trick, our little k is the same as this big k. All right, that was easy. Now, one of the really interesting things about this bound is that
that lesson is supposed to be experiment. The last line.
Yes, sorry. Thank you. Because this is minimal. Thank you. So one of the interesting things, again, about this is that it depends on k. And so what will happen is in the graph of n and the plot of n versus n prime, you'll get these regions. The graph is divided into these regions based on the number of factors of your number. So I printed out a few plots that I made. This is the first 10,000 numbers and their derivative. So that's the spec. It's pretty crazy looking. But what you'll notice, what you'll notice is you have these triangular spires, you have these regions like this, where there are points contained within that, and then there's a gap, and then points contained within this one. And these correspond to those different k values. Now, another thing that you'll notice in those plots, which I can just leave this up, which seems strange, is that you get these very, very solid lines that you feel like you shouldn't get. But they're very clearly straight lines that appear in those plots. Which brings us to our second property. Let's see, here's this one. Alright. So our second property is that I'll use phi. Phi is nonlinear in general. But linear for some pairs. So what does this mean? So if we take some particular pair AB, we can get the fact that A plus B prime equals A prime plus B prime. And not only that, but there's a theorem by Mirovsky. And this is, I think, also 2003. And this theorem is that this is the case, and so C, if you multiply by C, that it still holds. CA prime plus CB prime. But it takes it even further, and if this is an inequality, the inequality holds. So if plus b less than or equal to plus b. Less than. And you multiply by c to both. And the same for greater than. So that's something that's really interesting. It's the ratio of these two values that maintains linearity or sublinearity, makes it so that these things hold consistently. And that explains to some extent why in this graph you see these very strong lines, and they tend to be on the edges of these triangular regions. They tend to push things either above them or below them.
I'm a little confused about the theorem, what you wrote with 2 and what you wrote with your theorem. So
What?
phi is not linear in general,
So
but there are values of A and B which is linear, and then if they are linear, then
yeah, so
every C satisfies that.
exactly. Yes. So this is for any C.
But the assumption is if A and B,
If A and B are
if that
Sorry.
thing holds. That is possible.
if this
But no.
then
If that.
No, you're not. Is the bottom one true in general?
so no. This is only the case when A and B are linear. Or no, yeah, this is true. Sorry, this is true. If this is the case, then this is the case. If this is the case, then this is the case. Right. So the equality or inequality of this expression, whatever this symbol is, how they relate, that carries over if you multiply it from by a constant. Right. Sorry, that was confusing. Right. How much time? Okay, so that's fine. The last property I wanted to give is actually connected to this teaser. and I wasn't planning on going much into it anyway. But the last property is that this definition of the number derivative can be extended to different domains and ranges. And the biggest point is this right here. If I change what this x of I can be, then I change what the domain can be. I also have to define the derivative of -1 is 0, just like 1. And then I can extend the number derivative to all of the integers, to the rationals, to the irrationals. I don't know. And what I ultimately want to do, and this is what I'll talk about in this, is to extend to some level of the complex plane. Is this possible? Can I extend to complex numbers? So often complex numbers come up when solving regular function differential equations. And so I was curious if there was a way to connect that to complex numbers solving these differential equations. So constructing a complex number derivative would be subject to that talk. But the fact that you can do this is an interesting aspect of it. So there you go.
Are there any more questions before we jump into feedback?
I have a couple of number theory ones, but I'll just ask one.
Yeah.
Is there anything known about sort of the long-term, like asymptotic behavior of this?
Yes, so that's, I was thinking about talking about that. I decided not to, but yeah, there is. So in general, if you treat this math as a dynamic system, so you take repeating derivatives, then you either get, everything either goes to 0 or blows up. Now that's sort of a conjecture, it's sort of known, it's kind of between they know it for sure for most numbers, but they're not saying it for sure. And what's interesting about these extensions is they know for sure, for a fact it's true about the natural numbers, they don't know about the rationals. So once you extend it to the rationals, it's not known if that's the case. It gets a lot more complicated talking about those long-term asymptotic behaviors. Again, on that subject, the stable numbers, so think like 4 and the p to the p fixed points. Anytime that you have this times some number, it follows a very naturally depicted sequence as you take number derivatives. So n prime is some C1 times p to p, double prime C2 p to p. And so you get this really natural progression given any p. Is that answer?
Yeah.
Yeah.
What was the Putnam question?
So the Putnam question, they gave the two properties that phi of 1, the function of prime gives 1, and then it follows this Leibniz rule, the product rule. It's not been up there anymore. And it asked to give a definition and show that the asymptotic behavior of the derivative of 63 give what that is. So as you take infinite derivatives of 63, what do you get? And I believe it's 0. Because it's either 0 or infinity, so I'm pretty sure it's 0. Any other questions?
Do you know if those are strict bounds?
Strict bounds?
Like it attains equality somewhere.
So-
There are numbers where that is equality.
I know that they are not strict bounds. This is actually an improvement on another bound, as is this. The original bound that they had for the upper one came from number theory. It was originally in log base 2 of n over 2. Was originally what they had in there. It was Western who found that you could reduce it to this factor of k. And that was really interesting because that meant that it's not only limited on the bottom by k, but it's limited on the top. which is why it has that strange kind of spirographic. But they're not strict lines. Not, no,